Fly, 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 we fly through the sky. New frontiers can open our minds. No, we're not so far from that dream. Energy brings us life. Running out the midnight, bright lights, super love, until the twilight, the bright skies, super love, up to the moon, we will go beyond our reason tonight.
Right. That I love that music. It's jazzing me up every time. And this is another great opportunity for the Meta Visionaries to host another excellent lecture. I hope everyone had an opportunity to see Scott's wonderful introduction to satellite applications because we're going to delve much more deeper into the topic. So once again, let me introduce my very good friend, Dr. Scott Madry, professor at the University of North Carolina, Chapel Hill, and his topic is remote sensing, the introduction to. Thank you. Scott, take it away.
Excellent. Thank you, Jim. Thank you so much. Hello, everybody. It's me again, and I'm back. And I'm going to talk to you about a subject very dear to my heart, something that I've been, it's embarrassing now, professionally involved in the past 45 years. And this is the domain of space remote sensing. And look down here at the bottom of the slide, Arthur C. Clarke, again, one of my great guides throughout all of this, had three laws, and his third law was that any sufficiently advanced technology is indistinguishable from magic. And I'm going to show you some truly magical things of what we can do when we can harness our concepts of space and our ability to harness space technologies for the benefit of our planet. So, the objective today is for you to understand what is remote sensing, where does this come from, how does it actually work, and then how is it used, and what are some of the issues that are involved in our ability to do this type of work. As I mentioned briefly in our last lecture, remote sensing has fundamentally changed the way that we think about our planet home. Satellites have provided a great stabilizing capability for our planet geopolitically in what are euphemistically referred to as national technical means, and those are spy satellites. And you can see an example of a aircraft carrier here with a very high spatial resolution satellite image, an aircraft carrier under construction. And this used to be strictly the domain of national military and national geopolitical capabilities. Only a few nations had them, but now today we have many commercial and national systems. And all of this fundamentally is a good thing because it allows people to be able to see the world, to understand what everybody's doing, and it's a great stabilizing factor in our planet. So, why is this important? Why am I going to take all of this time to explain this to you? Well, remote sensing is a very powerful capability. It gives us the ability to understand and analyze and manage both our Earth and other planets and celestial bodies as well. It's a very interesting, a complex, and interdisciplinary topic. It combines all of the fields of fundamental science, of engineering, of systems engineering, of orbital dynamics, of applications, and it has real commercial space capability in there. Thousands of people all over the planet, people in your country, wherever you are, who are working in the remote sensing industry, either commercially or in government agencies. These provide real jobs and real environmental benefits to all of the planet. So here's a beautiful image, a nighttime low light image of the Middle East, and you can see lights on. You can see that gives us a great indication of where people are living. And be sure to think about this in terms of look at the Nile River, the lower uh, Nile River here, and you can see all the settlements along there and the massive settlement in the Nile Delta where it approaches Mediterranean. You can see basically where people live and where they don't. One of the things I love about remote sensing is it's just really beautiful. It's incredibly beautiful. It's art in and of itself, as well as being of great practical value. So let's talk again a little bit about satellites. Here we have some information. I have the URL down below, so you can go and look at this at your leisure. But here we have three different ways of using the satellites by nation state, by purpose, and by user. And so you can see the large one in the center that we have approximately equal numbers today of remote sensing and telecommunications satellites. And this is very different than the past. We used to have many more telecom than remote sensing, but as I mentioned before, our young friends at Planet now operate the largest commercial constellation of satellites for remote sensing with over 200 in operation today. You can see down here on the left that the United States is by far the largest operator of satellites, followed by China and Russia and other nations. Then here again, you can see how many satellites are commercial, government, military, etc. So this is just kind of where we are right now, and it's all changing quite rapidly. But I want to go way, way back. All of my degrees are actually in anthropology and archaeology. I'm fascinated by the study of us, Homo sapiens. Are we? Where did we come from? How did we become a space-faring species, these primates who millions of years ago migrated out of Africa and populated the world? Who are we? How did we become a space-faring species? We are primates. We have binocular vision. We're hunters and gatherers, and people throughout history in every part of the planet always wanted to find that hilltop view. We've always sought the highest place on the landscape, and in many cases, we've fortified these. And I've used satellite remote sensing to study and find. I found hundreds of archaeological sites using space technologies and images, and human beings have wandered across the landscape, and we have always looked for the high view. We looked for that hilltop where we can look down, we can see, are there migrating game that we could hunt? Are there potential threats to us down on the landscape? And we've created maps, and I'm fascinated by, and I love old historical maps. Excuse me. They're fascinating constructs, and there's a wonderful history of the development of cartography and the 15 and 100 human beings developed technologies using stars, using our knowledge of the world, the sun and the stars, and we've mapped the world. Human beings not only have wanted to observe our world, but we've mapped the world. And here we have a, a Dutch map from 1661 of the Arabian Peninsula. So human beings have always, as long as we have been exploring our planet, have wanted to find ways to map and study and understand the world that we live in. And there have been many early remote sensing systems. These are not jokes, these are actual real systems. A gentleman uh, used miniaturized systems and put a camera with a timer onto homing pigeons, would take the pigeons off and the pigeons would fly home. They would actually take aerial pictures. And in the 1700s, the French developed the ability to use gas balloons. And I know that Jim Green is very interested in this topic as well. And in our American Civil War in the 1860s, were some of the first uses of hydrogen filled balloons. You see the picture here for observation. And again, there's this relationship between remote sensing technology development and the money to develop this and military and national security requirements, but it always ends up coming over into the commercial domain. So as soon as technologies develop, people have used these to try to take pictures of our world. This is a very timely picture. This is a aerial photograph taken just after the terrible 1906 San Francisco, California earthquake and fire. This is a very topical issue right now for the terrible earthquakes and aftershocks that we're having in southern Turkey and Syria right now. You can see on the right camera that was used. This was used with a box kite camera. You can see at the bottom right, there's a series of these box kites, a dozen box kites, huge things that rise up and carried this camera aloft. And it took these incredibly detailed pictures of the utter devastation of what had been the thriving city of San Francisco. These images were taken by train to the East Coast, to Chicago and New York. They were put into the newspapers. And for the first time, people all around the planet were able to see the devastation. And this drove a great deal of the aid that was provided after this. And we're doing exactly the same thing right now as we speak in Turkey and Syria. There is this relationship between remote sensing and military technology development. World War I was the first real massive use of aerial cameras. The Second World War had huge increases in development in the types and sizes of cameras, development of infrared sensitive films. And here we can see some British air photo interpreters. And in the middle of this, you can see at the top middle, this is one of von Braun's launch sites in Peenemünde, and that's an A4 rocket getting prepared for launch. The bottom center image you see is that same location after the British discovered it and bombed it to take that out of operation. So we have this relationship between national security and military uses of remote sensing that has been with us since the earliest days. And our first satellite remote sensing systems were all derived from Cold World military requirements by the United States and the Soviet Union. All the civil systems that we operate today are the direct descendants of these first original Cold War systems. And it's a very little known fact that the Vostok spacecraft that Yuri Gagarin flew in, which is shown down here on the bottom right, was exactly the same spacecraft as the Zenit Russian photo spy satellite. And the Russian Politburo did not give Korolev the authority to launch Gagarin until he had successfully launched the first Zenit spy satellite. At the same time, the United States was developing their Corona spy satellite system. Both of these are being operated at the same time to provide this ability to look behind the curtain. And as I've said before, together, these provided an extraordinary stabilizing factor in a very dangerous period of our world history. So let's talk a little bit about the fundamentals of space remote sensing. We've had already excellent lectures by Jim on orbits and on the spectrum and electromagnetic energy, and we harness these in order to do remote sensing of our planet today. So, what is this anyway? Well, here's a textbook definition. Remote sensing is the science and art. It's very much an art aspect of this, of obtaining information about some object, some area, some phenomena through the analysis of data acquired by a device is not in contact with that phenomenon. Okay, so it's remote and it's sensing. All the space science that Jim and his folks do looking out are using comparable systems. And so here's my joke version of remote sensing. Here's a bunch of crazy guys running the bulls in Pamplona in Spain every year. Please don't go do this. And you can see this guy here is doing what we call direct sensing. Here's a bull. This guy is acquiring energy, much more energy than he was planning on. He's acquiring energy directly by being in contact with this bull that's not very happy about it. This guy sitting up on the fence here with this ancient old VHS video recorder that sits on his shoulder is doing what we call remote sensing. And so there are times and places when remote sensing is really a better option. For example, in when we've had these unfortunate nuclear power plant uh, disasters, we can send remote devices in places where it's simply not safe. And of course, for our space science colleagues, they don't get to go to Io. They don't get to go to Jupiter, at least not yet. But we can study these by studying the electromagnetic spectrum that Jim Green talked to you about. And we have developed many systems to do this. Human beings are extraordinarily clever, and we have come up with many different remote sensing systems, and these operate again primarily in two different orbits. We have the low Earth orbit polar systems, and then we have the weather satellites that exist out in the Clark geostationary orbit, along with our telecommunication satellites. And in the early days, when I started this long ago, there were only three commercial remote sensing systems, two Landsat and one French spot system. But look at this today. This is actually a little bit out of date, but look at all the civil remote sensing systems that we have. These are a large number. And look at all the different nations. It used to be only the US and Europe and the Soviet Union in China, but look at all of these nations that are operating space remote sensing satellites. And that was the optical or passive systems. These are the radar satellites. Talk more about the difference between these. You can see that again, we have many different nations have developed and operate these satellites for remote sensing purposes. So I want to ask you all a question. Why are there so many of these? Why do we have so many satellites? And essentially, all of these are pretty much doing exactly the same thing. They're doing exactly the same purpose, similar design, measuring the spectrum in the same wavelengths. And the question I want to ask is, why do we have so many? And while we do that, I'm going to make everybody do a wave. So you wake up. So come on. I want everybody, we'll start over here on this side. Let's do a wave. Come on, all you folks at home, everybody get up, do a wave, shake it out a little bit, wake up because I want you to be aware and thinking about the questions that we're facing. And so the answer to these questions are many. Every country wants to operate their own systems for many reasons. Primary reason is dual use and broadly defined national security. But we have many other reasons as well. National pride. Minor spacefaring nations want to have their own satellite in orbit. They want to operate their own satellite as an aspect of national pride. And this is entirely understandable. People want to have their own systems. They want to launch a CubeSat, take pictures. Other reasons are for doing natural resource management. For example, Brazil has been a leader in developing their own satellites to be able to monitor the deforestation in the Amazon, just as one example. But there are other reasons as well: economic competitiveness, national technical capability, supporting education, research, commercial benefits, jobs. There are lots of reasons why we have so many competing remote sensing systems today, and there will be many more in the future. The platform is separate from the sensor. So we can put a remote sensing sensor on any number of different platforms, all the way out to geostationary, or as Jim Green showed you, out at the Lagrange points where James Webb, who was a graduate of my university, the University of North Carolina in Chapel Hill, I'd like to point out, we can put satellites in geostationary orbit. We can put satellites in a polar sun synchronous orbit so the Earth rotates underneath the satellite and it images the entire planet every certain number of days. We have lots of remote sensing systems on space stations operated by humans, high altitude aircraft, low altitude aircraft, UAVs and little small systems, all the way down in situ sensors on the ground. So we have and can put sensors on a variety of different platforms, all the way from in situ on the ground, all the way up to geostationary. It just depends the kind of data we want to acquire and the frequency of the data that we need to collect. One of the most favorite things on the International Space Station is the ability to do photography of the Earth. And Jim Green and I have been lucky enough to know and work with many astronauts from many different nations around the world. And the one thing they all say they love to do is to pick up that camera and have a chance to look out the window. They have cameras with very large telephoto lenses, and they take beautiful images, and over 1 million images taken from ISS are currently up online. And you can go to this website, search them, and look at these incredibly beautiful images. All these people up there, this is the thing they all really love to do. Here's an example. This is a nighttime photo of Riyadh taken from the space station on the night of November 13th, 2012, and you can see the electric lights. You can actually see the different kinds of electrical lights. You can see the areas like the university up in the northeast corner, the ring roads. And it's incredible the kind of detail that we can see by taking images at night. Another key aspect of remote sensing are our weather satellites that live out in geostationary arc. These live out there in the Clark orbit with the telecom satellites. And this is the kind of image that they see, and they're constantly staring at one face of the Earth. This is a European UMETSAT satellite image, and this is what it sees. And it sees the one entire face of our planet constantly. And we have a ring of these satellites, two operated by the United States, two operated by Europe. We have satellites in the geostationary ring operated by India, by China, by Japan, and by Russia. And together, all of these give us a constant view of our planet. And basic science like weather, cloud dynamics, ocean currents, all of these things are using these satellites. And so this is a Meteosat image, again, the European satellite. And this is, here we can see a dust storm sweeping across the Arabian Peninsula. And if we're lucky and it works, I want to show you a movie, a brief movie that was taken on March 26, 2011, where the European Meteosat observed a very large dust storm racing across the Arabian Peninsula. So let's take a look at this incredible movie. This is the kind of thing that our geostationary satellites show us each and every day. So you can see the storm building up here, and here it goes racing across the entire Arabian Peninsula. And you can see how storm after storm, century after century has scoured the Arabian Peninsula. And you can see the effects of this in this storm racing across and finally dissipating once it reaches the Indian Ocean coast. And our satellites are constantly viewing our planet everywhere, uh, looking for severe storms, looking for hurricanes and cyclones. And these are vital aspects of our ability to observe and monitor our planet for long-term climate change, but also particularly for disaster management. Isn't that cool? Okay, so we have many different kinds of remote sensing satellites. We have satellites of different resolution. Our geostationary satellites have constant view but lower resolution. Here is a NASA satellite called MODIS that operates on a satellite called Terra. And this is a 1-day composite. So you can see that this MODIS sensor has a moderate spatial resolution, but it is able to acquire data for almost the entire planet each and every day. Look at the cloud patterns, look at the dynamics of the vegetation, of weather. These data are vital for understanding what we call Earth system science, the understanding the complexity of the interaction of all the different components of spaceship Earth. We have other more detailed satellites. I spent many years of my career working with NASA's Landsat satellite data, originally 80 meters, then 30, then 15. And here we have a composite image of the Arabian Peninsula. This is a cloudless mosaic Landsat. And you can see that this is extremely useful for many different kinds of applications. And in fact, up here above us, we have the Landsat 7. This is the satellite directly before 8. This is exactly what some of these remote sensing satellites look like. So you can see, based on your previous lecture, uh, the components. You have, of course, the single photovoltaic array that provides power. Over here, you can see 4 different small dish antennas, which telemeter the data down to the ground. This is the bus on the bottom. And then here on the top, you can see the different sensors. And so these are the sensors over here next to me, the 2 different sensors that are observing the planet. So the satellite is flying in this orientation. Okay, it's looking down. The sensors here are pointing down at the Earth. The 4 different uh, dishes here are communicating, telemetering the data, and the solar array is acquiring the electrical energy to power the system, and it's flying along in an orientation like this. So we design and build and operate these satellites, and they give us extraordinary amount of data. And people all around the planet are involved in studying these in a wide variety of applications: geology, agriculture, water quality, archaeology, wildlife management. Virtually every academic scientific discipline is capable of acquiring data. And here you can see, here's our Landsat 7 image of a large portion of the Arabian Peninsula. You can see here these ancient dark lava fields, which are very easy to discern visually from our image. And this is the kind of thing that I've spent much of my career analyzing. Today, we have a new revolution in very high spatial resolution capabilities, a revolution. This is a US system called QuickBird. And here we have an image taken back in 2005. And you can see it's a very small satellite, much smaller than the Landsat. And look at the kind of spatial resolution that we're capable of seeing. So in the past, these were only very secret military systems. Now we're commercially imaging the entire world every day, and it's a good thing. People always ask me, how good can it get? Here's a very high resolution commercial image. This is the old satellite, or the space shuttle Endeavour, sitting on launch pad 34A at the Cape. You can see here's the orange external tank, 2 white solid external boosters. Here you can see the flame trench. You can see high level of detail. And this is the kind of data that we get routinely every day. We have commercial satellite sensors today with a spatial resolution of 0.5 meters or less. And think about all the things that we can do to help monitor and manage spaceship Earth with data that goes all the way from less than 0.5 meters up to our geostationary satellites, able to look at the entire planet. And we're undergoing another revolution in capability, just like in the telecommunications world with Starlink and this mega constellations. We have these young kids from California who founded the company Planet. They literally founded it in a garage in Silicon Valley, and it's these young kids who revolutionized our world. They have over 200 of these tiny little 3U satellites that they developed, and they are operating the world's largest commercial remote sensing constellation today. And it's amazing, and they're changing the world. They're changing our ability to monitor our planet. And it's a good thing. So we have two basic kinds of systems. In remote sensing, we have what we call passive and active systems. Passive systems are systems like Landsat up there. What these are on the top, we have the sun. The sun's emitting its electromagnetic radiation in all bandwidths, as Jim Green explained. Tiny fraction of that energy is coming down and hitting the Earth's surface. It's being reflected or re emitted by the Earth's surface. And a tiny little bit of that is directed into an optical telescope, just like Galileo had, a little bit better, and focused onto a detector array. That detector senses the amount of energy which has been reflected or emitted off of the Earth's surface. It stores that, sends that back down to the ground. So these are what we call passive systems. They use the sun's energy to record the amount of data which is interacted by the target Earth's surface, and it sends that back down to the ground. We have a different class of satellites which operate in the radar, excuse me, or microwave range. And these are very different in that they send out their own bursts of electromagnetic radiation down to the ground and then measure the response that they get back. The benefit of active systems is that they can be used day or night, rain or shine, through clouds. Active remote sensing systems, again, originally developed for military purposes, now commercially available, can operate day or night, rain or shine. And I worked on a project many years ago. Uh, I was doing mountain gorilla habitat research in the Virunga volcano region of Africa and Rwanda, Uganda, and the Democratic Republic of Congo. And we had never been able to acquire a single Landsat or spot image because it was always cloudy. With NASA, we flew the SIR-C, the shuttle imaging radar, on the space shuttle twice, and I was fortunate enough to be able to be an investigator on that mission. We were required, we were able to acquire satellite imagery of the region where these mountain gorillas live for the very first time because we were able to use radar active remote sensing. So here's an example of some passive systems. This is Adelaide, Australia, where I was just down teaching a couple of weeks ago. Here's the city of Adelaide in the center of the image. It's got a beautiful park system that surrounds the entire city. Down here on the bottom right is a series of the Adelaide Hills, mountain region, and the coast is on the very left edge. So the image on the left is what we call a true color image. This is what the world really looks like if you were up there. Vegetation is green. The image on the right is a color infrared image. And if you remember from Jim Green's lecture on the spectrum, our eyes are only able to see a tiny little bit of the spectrum. There's a whole lot more energy out there. We don't know what color infrared is, but we can design sensors which collect the imagery in the infrared spectrum, and we arbitrarily assign that to a color red. So the red color you see here on the right is actually invisible infrared energy that we have been able to acquire, and we give it a color because we don't know what color infrared is. Here's the same place, but two different radar images. These are active remote sensing images in the microwave region, much longer wavelengths. We're bursting down a blast of microwave, a very coherent microwave energy and measuring the response back. And the variation here is because we're looking at two different angles. And so all of these systems are very complex engineering, but they acquire very interesting, useful data. As I mentioned before, we operate primarily in two different orbits for space remote sensing. The geostationary satellites out at that magical Clark orbit where they hang in the sky, and we can put a ring of these around the Earth like a necklace, and we're constantly looking at the Earth from out at 36,000 kilometers. The other primary orbit that we use is a very particular kind of an orbit. It's what we call a polar sun synchronous orbit. And in this orbit, we put our satellites into a nearly perfect polar orbit. It's a little bit retrograde, it's a tiny bit more than 90 degrees. But what this does is it allows the Earth to spin underneath our satellite as our satellite is sweeping around. This lets us acquire imagery of the entire planet from our sensor every certain number of days. So think about the Earth as being a large orange. We have a tiny little knife and we're sweeping a tiny little bit of that peel off every time the satellite passes over. And the Earth is rotating underneath us, and every n number of days, depending on how wide our sensor is looking, we're able to acquire imagery over the entire planet. So these are the two primary orbits that we use in space remote sensing. And again, our friends with Planet have revolutionized this. And I would like to show you very briefly now. Remember in my last lecture, I showed you our Satellite Explorer website. I'm going to ask them to queue up the video, and I want to look here quickly and show you some of this remote sensing information from our Satellite Explorer website. Howdy, partners. Your old buddy Scott here again. I want to talk to you about remote sensing satellites, Earth observation satellites, and we're going to go back to our website, Satellite Explorer, and we're going to use this as a way to explore the domain of Earth observation satellites. And so what I'm going to do is I'm going to click over here on purpose, and I'm going to go down and click on Earth observation. And this shows us the primary orbits that Earth observation satellites utilize. And you can see very quickly there's three primary orbits. We have the geostationary orbit. This is the domain of the weather satellites, the satellites that are out there constantly monitoring the planet, looking at the Earth's weather and climate. And then we have the low Earth orbit satellites, and you can see, I'll zoom in here, and you can see that very close to the Earth's surface, we have a huge number of satellites in LEO, low Earth orbit, which are constantly orbiting the planet and looking at our Earth. And then we have this third class, which is somewhat unusual. We have these satellites in a very high elliptical orbit, and these are primarily operated by Russia. And these are satellites that have a very, almost like a Molniya orbit, and they're used to observe the Earth in its low portion of the orbit over here. So in Earth observation, we have currently right now, it says 947 satellites, almost 19% of all the working satellites. And one that I've worked on many times and used the data my entire career is the Landsat data, a fantastic program first started in 1972, the first civilian natural resource satellite system, and it's still operating today. It's a fantastic system. And let's go and let's look at, here's Landsat 8, right? And you can see right now where it is. This is real time from when I recorded this. And you can see it's passing across, it's on an ascending part of its orbit, and it's up above in the Indonesian and heading up towards Thailand. And so we can look at where all of these different satellites are, and it's a great tool for us to be able to learn more about what all of these things are. So I'm going to go again and click on Earth observation satellites, and let's look at Planet, the Planet group. They're young people out of California who've really revolutionized how we do remote sensing. And here are their constellation of satellites. And they actually call this a line scanner for the planet. And every day, all these satellites just come down like a line scanner printer and image the entire planet every day, every day. So we get data acquired every day over the entire planet from these. And Planet Labs today has over 200 satellites operating, and they're tiny little things. They're 3U cubes. It's brilliant engineering, and they're really fantastic. It's a wonderful resource, and I use their data all the time in my research. So let's look again, and we'll look at just a couple of other opportunities there, but I just wanted you to see in the Earth remote sensing world, we have the geostationary satellites out here. These are the weather satellites. We have the just a few of these highly elliptical satellites operated by Russia. But when we zoom down close, you can see that the Earth is constantly being monitored by these satellites, and the data is provided to us for a variety of different uses. Okay, let's go back to our lecture.
All right, about that. So how does this happen? How can we do this? How can we actually get these incredibly beautiful detailed images from a satellite 800 kilometers up in space, moving at over 8 kilometers a second? How can we do this? How does this happen? And the answer is we have some fundamental physical processes that are going on. And this is the most important part of this lecture. Objects that are related in physical form can be detected and described by analyzing the pattern of energy reflection and absorption in different parts of the spectrum. So this chart shows you that water in blue is absorbed or reflected back in different parts of the spectrum. In vegetation, what we think of vegetation as being green, right? But in reality, vegetation is not green. The photosynthesis process that drives the process of life in vegetation, it actually is the fundamental basis of all life on our planet. The process of photosynthesis uses primarily light in the blue and red parts of the spectrum. It doesn't want the green light. So plants reflect off green energy. And so we see plants as green because that energy is being reflected off of them. And in fact, there's a huge spike in reflection in vegetation just outside of our visible eyes in the near infrared. That's why we want to have sensors. See, the little triangles here are where we have sensors because we want to measure these processes. So we call these things signatures, spectral signatures. And water has a unique spectral signature, and palm trees has a unique spectral signature. Everything, this planet and every other planet, has a unique spectral signature, which is the way that it absorbs and reflects electromagnetic energy in different parts of the spectrum. And that's how these systems work. We have in these satellites sensors and detectors, large optical telescopes that look down at the Earth. We record the light that is reflected. We store these data on board our satellites as zeros and ones. We telemeter these down. The researchers and scientists and applications people on the ground. And then we use this knowledge that we have in order to measure and model and understand our world. And all of these data come down in what we call a raster data format as pixels. Here we see a sports stadium viewed in very high resolution, and you can see the squares. And each one of these squares actually has a number which is representative of the amount of energy that was reflected off the ground into our telescope, into our detector in that part of the electromagnetic spectrum. That's how this works. And so you can see in this chart, we have three satellite systems. The top, the Landsat 8 and the Landsat 7. And Jim Green explained to you about how our atmosphere absorbs electromagnetic energy in certain parts of the spectrum, and we can't collect data in those parts. So you can see here in this chart where we have sensors in the blue and green and red and near infrared and thermal bands. They're clustered only in areas where our atmosphere allows this energy to come down into Earth's atmosphere. So the future of all of this stuff is this whole domain of what we call geomatics. And this is where we take all of this data from satellites, from in situ measuring systems, from positioning systems, our computer analysis and modeling, our visualization technologies. A lot of this is being driven now by AI and expert systems. And it's the functional integration of data taken from many different satellite systems, from terrestrial systems, from airborne systems. We can put all of this stuff together, preferably in an open source type environment. And this is how we are going to be able to address the complex, important issues facing spaceship Earth: public health, disaster response and mitigation, agriculture, water quality, public safety, planning, wildlife management, cultural resource management. All of these things are made possible today and are going to be incredibly more capable in the very near future because of our ability to harness, integrate data from all of these different types of sensors, use our advanced modern computing capabilities, and then apply them to the needs of the people of the planet. I'm a big believer, as I told you before, in open source. I use a wonderful toolkit called QGIS, which has remote sensing and GPS and spatial modeling and analysis. It's all free, runs in 40 different languages, including modern Arabic, and it's free. It's free as in lunch, it's free as in liberty, and it's a toolkit that lets us harness all of this capability. Saudi Arabia is becoming very active in these areas. King Abdul Aziz City for Science and Technology has developed and manufactured two high resolution Earth observation systems launched, operating today. And there are key points that I want you guys to remember. Satellites, our ability to understand the physical processes of the universe, the fundamental basic science that Jim Green and his colleagues have done, going all the way back, not just to Galileo, not just to Newton, but the ancient Arabic scholars of the 7th and 8th centuries, the ancient Greek and, and Chinese, Indian scholars, the shoulders of giants that we reside upon today. Our ability to harness these and to engineer and design and build and launch and operate satellites that acquire this incredible amount of data provide tremendous commercial, they provide tremendous national security and stability benefits. To my mind, much more importantly, they're a public good. These satellite systems like Landsat in continuous operation since 1972. The data are free. It's freely available on the internet. Anyone can go online and get them. You can use systems like QGIS to analyze these, and these provide us with the ability to understand and manage spaceship Earth. It's the only one we have. It makes space relevant for all of the peoples of the Earth. So that's what I wanted to say to you. There's a lot more that I could talk about in remote sensing, but we only have so much time. So I'll leave it right there, and we'll see if we have any time left for any questions or discussions. I would love to talk to you more about what all this stuff is. Thank you very much.
So, Scott, I think we have time for one question. What could Earth observing constellation with the number and satellite size of Starlink 2.0 be capable of?
Oh, yes. Planet Labs today, or Planet, operates just over 200, and they are able to image the entire planet every day. But if we move to a system, for example, where we have thousands of satellites that are that would provide us with a virtually constant view of the planet. Uh, Planet can look at the planet every day, but sometimes it's cloudy. Whereas if we had these mega constellations with micro miniaturized sensors and optical assemblies, we could literally be making movies, visualizations, real time movies of traffic, of water flow, and especially, I think, most importantly, in the field of disaster management. It would give us a powerful tool to better able model, prepare for, and respond to the kinds of disasters that sadly we face all around the planet. And it's not just the sensors, it's not just the satellites, it's the entire complex overall system, including the data analysis, modeling, computing, AI, expert systems, all of this stuff integrated together is what actually drives the future of all of this. So I hope you found this to be interesting and useful. And I look forward to giving you my next lecture on the area of satellite telecommunications. I think, yes, do we have one more question behind you?
I'm,
Hi,
I
Scott.
got a question.
Yes. I would like to ask you regarding
Can we put a satellite in some synchronous orbit, but with an altitude of 36,000 kilometers?
Oh, sure, sure. It will be what we call geosynchronous, but not geostationary. The geostationary orbit, the Clark orbit, is a very unique, specific version of a geosynchronous orbit. And the difference is that the geostationary orbit, that's the one where the satellite just hangs there in the sky as the Earth rotates, is at an inclination of 0. So it is an equatorial orbit. That's a very special orbit, but we do have and we do put satellites into exactly the same uh, altitude, but if it's inclined above 0, then it is the satellite does not hang there. It will actually make a motion in the sky. But sure, we can put satellites in a polar orbit, but it will not be a sun synchronous orbit. The polar sun synchronous orbit is a specific combination of the orbital inclination, slightly retrograde, and a low Earth altitude. If we put it up into a geo altitude, it would no longer be sun synchronous.
Thank you, Scott.
Okay,
Okay,
we'll
well,
talk to
yeah,
you guys
thank you
again
so
soon.
much, Scott. Yeah, thank you so much. It's been great. Another super lecture. And once again, in a half hour, we're going to be back with another one, last one today, which is going to be, as Scott said, satellite communications. Thanks again, Scott. Super. Really enjoyed it. Yeah.
There we go.
Flames inside, leaving all behind us. Better visions are flying, galaxies and beyond. In space we merge with science, technology with no guidance. And then we travel so far away. Fly, 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 we fly through the sky. New frontiers can open our minds. No, we're not so far from our dream. Energy brings us life. Running at the midnight, a white light, supernova. Oh. Until the twilight, the bright skies, supernova. Oh. Up to the moon, we will go beyond our reason tonight. Going, 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 going.